Good afternoon and welcome everyone to our second webinar on the 2DCC. Today we're going to be going over some opportunities and challenges in theory. The talk will be given by Vin Crespi. I'm Kevin Dressler. I'm the Operations Director for the 2DCC and I help to moderate these webinars. If you have any questions during the course of the webinar for those who are participating online, you may chat it to me in the chat box. Realize that these sessions are being recorded. So questions that you may ask in the chat box are live and people can see them. If you want to just send them to me privately to the host, that is fine, and then no one will know that you asked the question, but I'll moderate that question at the end of the session. There's also a local audience here today, so at the end of the session, I will moderate the online questions first, and then we'll have the local audience ask their questions. So without further ado, Vin Crespi will give his talk.
Thank you. Now, last week we had a webinar by Joan introducing the two-dimensional crystal consortium. So I'm not going to assume that you saw that talk or necessarily that you reviewed the information on the website, but I will go through that more cursory manner, of course, that Joan did last time. So I want to focus on opportunities in theory and simulation in the two-dimensional crystal consortium. This is a NSF user facility just ramping up, which supports synthesis efforts in two-dimensional chalcogenide systems. With user proposals and experimentalists coming here to grow samples on various pieces of molecular beam epitaxy capabilities and MOCVD and crystal growth, bulk crystal growth. The purpose of this talk, or the audience for this talk, is actually threefold listed on the bottom here. There should be theorists who are at Penn State who are looking for collaborations, support for personnel working on a theory project that aligns with the mission of the 2DCC, or computational support access to computational resources, again, aligned to the mission of the two-dimensional crystal consortium. Also theorists outside of Penn State, and welcome to those of you who are listening, who are looking for collaborations in the area of synthesis of two-dimensional systems, and also potentially access to computational support and travel support, in particular for individuals from minority-serving or primarily undergrad institutions for that last category. We're not an NSF grant-making institution. We can't send money to support people at other locations, but what we can provide is cost-free access to the resources here and access to the experts and expertise of the staff and the affiliate faculty in the 2DCC. And then finally, our third category in audience is experimentalists who are interested in using the facility to do growth of 2D chalcogenide materials, who are looking for theory support. You may have a question, something about the growth or some area that you want some potential theory input on, and you may be thinking, how do I plug in to theorists who can help me with this through the mechanism of the 2DCC. Okay. Now, of course, this doesn't work. Sorry, my slide advance is not working. We'll go to the old-fashioned way. Okay, so the heart of the 2DCC is experiment. The heart is the hybrid MBE system, metal organic CVD systems, and the furnaces for bulk growth. How does theory fit in? What we don't want to see happen is to see the theorists off in their own sandbox, working on their own problems, and not connecting to the needs of the experimentalists. If we're not making great stuff in those chambers, it doesn't matter what the theorists are doing. So let's think about how synthesis works nowadays on the experimental side. You know, in the broadest brush, there are many, many combinations of growth parameters that generally need to be explored, need to be examined to get a particular growth to be successful. There's so many complications of kinetics and heterogeneity that simply have to be examined, and that's, you know, essentially that's why I animated a pair of hands. A lot of this is the pair of hands exploring the parameters of the growth space. Now, of course, this isn't done blindly. This is done with a combination of inference and intuition, the brain and the gut, right? And good growers work really hard and have really good instincts and have really good knowledge of their area of growth, right? All those things have to come together because it's so challenging to look through these huge parameter spaces and try to come up with the way of actually making the growth you want happen. It's very far from the equilibrium thermodynamics the theorists are most comfortable with. So what role can theorists play in that? Again, at a broad brush level, if our goal is over there on the right and we're over here on the left, theorists are not going to solve this problem for experimentalists. Right? What role can we provide? We can perhaps help fill in the map a little bit. So theorists could help guide this process of exploration of the parameter space, suggest particularly promising places to look to try to control nucleation, to try to control growth, etc. So our vision is the theorists are going to plug in, motivated by these real problems of growth that experimentalists have, not off in their own playground, and see if we can improve the efficiency, essentially, of this search. So what are those questions? So this is a synthesis and compilation of some of the issues that the experimentalists who will be using the platform have. And I put these up here in the theory talk because if you're a theorist and you're thinking about somehow plugging in to collaborate with members of the 2DCC to potentially get involved in some of the supported projects, you want to have these questions foremost in your mind. These kinds of questions. This isn't an exhaustive list, but it gives you a flavor of the things that synthesis experts have foremost in their minds. What you'll see here is a lot of it comes down to two combined issues, kinetics and heterogeneity. That nucleation, if you want to grow single layers rapidly over very large areas that are single crystals, you absolutely have to control the nucleation process. This is something that, frankly, theorists try not to worry about too much, atomistic theory and simulation, because it's so hard, because it occurs in some, potentially at a defect on the substrate or some special geometry, and the geometry of the nucleation site may be very different from the geometry of the actual 2D layer that you're making. The seed may look nothing like the final layer. There are all sorts of questions about the precursors. As a theorist, you may think of sulfur as a chemical potential and not worry about anything else. As an experimentalist, you may worry about whether the sulfur source is a long-chain sulfur, something that's cracked, a sulfide, some more complicated species, because it controls the kinetic processes by which that sulfur gets incorporated. It controls rates, it controls side reactions, it controls how rapidly you may nucleate a second layer on top of the first layer, which may be very undesirable for what you're doing. It controls what temperature everything has to happen at, which then has cascading effects for all of the other components of your system. These are really complicated questions. Theorists are not used to dealing with this level of complexity, certainly not in the integrated sense that an experimentalist has to confront them all. But we certainly should be able to pick off one or two at a time and make progress in specific categories and specific areas. So again, the main purpose of this slide here is think in terms of these very challenging questions when you're thinking about theory, because these are the kinds of things the experimental users of the facility are going to run into roadblocks on, right? They're going to be trying to achieve some particular form of multi-layer growth or single layer growth, and they're going to run into problems with the nucleation or growth kinetics or some added components in the system. And if a theorist wants to be useful and provide guidance, you have to confront that complexity. Okay, how does theory support work? Or how, I should say more specifically, how do we envision it working in the 2DCC? Keep in mind that we're just ramping up and there is no existing example of a user facility devoted to synthesis of materials, 2D or potentially otherwise, of this character. So we're going to be figuring out how to make this system work and honing the processes as we go. So to answer this question, what I want to do is walk through a case study, in this case of an experimentalist using the platform and highlighting the interactions with theorists that could occur at different points in that process. And then think about how the system as a whole, the 2DCC, the platform, can facilitate that. All right, so notice also I list sometime in late 2017, and I'll look over at Joan and make sure that's not too aggressive. As far as when the experimentalist using the platform, the actual equipment has to be installed. So this is not something that could happen tomorrow, this case study. This is something that would require the MB systems and MOCBD systems to be installed. But I want to give you a case study on that time frame because that's really the core operation of the platform. Okay, so first, just a brief flow chart. The platform is access to the platform comes via user proposals that come in, and I'll be talking about our very first theory call, which is an unusual type of call. Most of our calls will actually be experimental oriented. User proposals will come in. After they come in, there will be a review process, there will be a selection process, and there will be an alignment and allocation process, meaning that proposals come in, they have to fit in with the equipment and the capabilities experimentally, they have to fit into scheduling, there may have to be a back and forth with local expertise as far as the exact procedures and strategies being followed, and there may also be theory needs or interests of the people proposing that we may want to facilitate some matchmaking on to try to get the right theory resources aligned to any given user proposal to help maximize its chances of success. So once that all happens, there'll be a set of initial experiments. One place theory comes in is what you could call proactive theory. In these initial steps, the user proposal, although it's an experimental synthetic proposal, there may be a supporting theorist who is a long-term collaborator of that experimentalist who builds something into that proposal. There may be a need that that experimentalist says, you know, I really could use some theory in this area, phase stability, in this area, nucleation kinetics. Maybe they have someone in mind, maybe they don't. But that could come in as a need identified, which then the personnel in the 2DCC may try to help address that need through some sort of coordination. Experimentalists or theorists are also available as consultants, essentially, to help design the initial experiments. There may be some characteristics of the sample, its thickness, its doping level, that particular theory expertise resident in the 2DCC could assist in determining and helping guide the particular parameters in the initial explorations. The platform has excellent in situ characterization and ex situ characterization facilities, which obviously will then come into play. There's the potential for follow-up experiments, and there's the potential for what one might call reactive theory. So imagine someone is, started doing these experiments, everything doesn't go right the first time, of course. So some roadblocks are seen experimentally, and there may or may not, depending on the circumstances, be an opportunity for a theorist to be helpful, right? In overcoming those roadblocks. Those are problems that may not be anticipatable at the beginning of this particular user project. They may not be reasonable to expect them to have been written into a user proposal, right? You can't anticipate particular things that are going to go wrong, but we want as a platform to have a way of reacting to that and supporting theorists' contributions towards this, ultimately the success of the experimentalists, right, of the synthetic efforts, because that's our overall goal. So you can see theory is going to fit in several places. It can fit in right from the beginning, or it can come in and get integrated in at a later date. And we want to have ways of supporting both of these mechanisms. Okay, so here's a case study. It gets very specific in places, but that's purely to give it some concreteness. This by no means is any limitation on the scope of what would be supported by the platform. In this case, I'm going to talk about an imaginary user who comes in wanting to study the quantum anomalous Hall effect. This is a quantum Hall effect that's seen at zero magnetic field, but it requires a sample to have magnetic order. And the original discovery in this system was a material that required an external magnetic field to create that magnetic order. So that's sort of against the whole spirit of the phenomenon, which is supposed to be quantum Hall effect without an external magnetic field. Then later, a material was discovered, which was chromium and vanadium doped bismuth chalcogenide films, that showed a quantum anomalous Hall effect at 0 external field. They had their own magnetic order, but you had to cool down to 100 millikelvin. So open questions here are the ferromagnetic order is actually at about 20 or 30 Kelvin. So why don't we see the quantum anomalous Hall effect up at those temperatures? Why do you have to go down to 100 millikelvin? And is there potential to increase the temperature at which this effect is seen? And I will mention here, I'll highlight in red everything where theorists get involved. The theorists here actually actively suppressed progress because the vanadium doping here was predicted as not being magnetic. The experimentalists in this case went and did it anyway, and it worked. So let's keep the theorists humble about that. Okay, so that's the scientific context. And now our user in our case study is Alicia Edgemode. She's an expert on neutron scattering and magnetic thin films. She hears about the capabilities of the 2DCC in part through a webinar like this one, but one which is specifically devoted to the synthesis of a particular materials class. That's the kind of webinar that will be coming up later in the tenure of the platform. Edgemode then gets intrigued by the possibility of examining a set of gated films that are 2D chalcogenide systems and using her particular techniques in neutron scattering to look at the doping dependence of magnetization and the depth dependence. She's also thinking potentially about some alternative rare earth dopants. It's an interesting idea if they happen to be soluble and if they happen to be phase stable. And perhaps she puts that idea into her user proposal. That proposal comes into the system, goes out for external review, is reviewed positively. The executive leadership team chooses it for support, which means now access, that Edgemode now has access to the synthesis facility. And Professor Edgemode then has interactions with the affiliate faculty and the staff in the platform, in the 2DCC, to help essentially coordinate and launch her particular user project. And in particular, this interesting rare earth doping idea is identified as potentially benefiting from some calculations on phase stability, for which there are local experts. So this project could be chosen for support with the 2DCC actually doing some matchmaking and potentially providing perhaps fractional graduate student time to examine this question in support of the project. So that's one way where theory support could come involved. It could come in dovetailed with an experimental effort. And then there would be computational support, access to computational resources provided as well. The idea here, the ultimate goal is to make our users as successful as possible, improve the odds of success. Additionally, there could be consultations, very simple things, consultations with theorists in figuring out the thickness of the sample. This could be something where someone like Chao Sheng, who's an affiliate faculty, has a conversation. Some of the theorist interactions could be as simple as a hallway conversation, potentially leading to deeper collaboration. And then initial results. So when initial results pop up, again, there could be some consultative interactions with the affiliate faculty. Beyond that, these phase stability calculations may now have borne fruit and revealed, suggested another potential dopant. So here the theorists are doing equilibrium calculations. They're providing a suggestion on a direction to go. It isn't a complete picture. It doesn't get at reaction kinetic issues, but it suggests a direction to look in this giant parameter space. And this is, as I said, a project where the personnel could well have been supported through the 2DCC, the theory personnel in support of that project. Now, just to emphasize here, there can be interactions with industry. On the theory side, facilitating those interactions is also valuable. In this case, in my case study, there's an interaction with Dow as opposed with regards to metal organic precursors. That's sort of a side note as far as theory interactions go. But you could certainly imagine theorists bringing industrial contacts in as well. So all of that was proactive theory. That was theory. The needs were identified from the beginning of the project. Some of the resources to support that were engineered into the project as it was initiated. But there's also reactive theory. There's theory, the need for which is only apparent after the project is in motion. So here, for example, perhaps the gadolinium doesn't go in. Maybe ZK did a great job on the equilibrium calculations, but there was a kinetic problem. And the gadolinium was clustering on the surface and not going in. That would be an opportunity to then bring in expertise in reactive force fields to actually model kinetics. So this would be a second major route by which theorists can get involved in the center, would be jumping at and attacking that kind of problem. Now, this could be something that's supported by somebody who has existing funded support from an external grant to support their personnel, or this could also be a situation in which personnel support is coming from the 2DCC itself or some combination thereof. You'll notice on this slide I have an example of the latter as well. There are, for example, there's a NSF research traineeship grant at Penn State, and you could imagine a student supported by that jumping in and doing some kinetic calculations. This is something the 2DCC absolutely wants to facilitate, is the interaction and collaborative interactions with theorists across Penn State and well beyond Penn State for certain, to attack these problems, because problems are really hard. Okay. Then you could imagine that and I should mention we have special expertise in reactive force fields here at Penn State, which could be particularly valuable. Both Audrey Van Duyn and Susan Sinnott, who have both developed very compelling reactive force fields across quite a wide range of material systems. Okay, so of course in my case study everything works, and the theorist simulations come and rescue the project and suggest a new organic ligand that reduces the clustering effect by releasing the surface sites that the gadolinium needs to incorporate at. And the project achieves success. So the success is dominated by the experimental capabilities, but facilitated by theorists providing insight and guidance at various critical steps to help improve the likelihood of achieving success. I want to mention that we envision the resources here that are developed, a new reactive force field, for example, as being then a community resource. And the new information on phase stability that's developed being a community resource. We'll be developing platforms and partnering with other platform providers in both of those areas in terms of the code and the data sets to develop a robust shared community set of algorithms and data that assists in two-dimensional synthesis of 2D systems. And a second thing I want to highlight here, which we're going to be navigating as the platform develops, is publication co-authorship. So as you saw through this process, there were potentially staff members at the 2DCC, collaborators and affiliate faculty with the 2DCC, interacting with users who are using the facilities. And throughout this whole process, there's going to be a question of co-authorship. And there's a very simple answer to that. We're be guided by the same criteria that are used in any scientific work. People who make a substantive intellectual contribution to the scientific result should be co-authors, and people who do not make a substantive scientific contribution would not be recognized with that distinction. Okay, that's a general overview, and that may sound very nice, but none of that experimental equipment exists today. That's being ordered and installed as we speak. So what can a theorist do today to help facilitate the launch of the 2DCC? And there, the question is, let's develop the tools and the data sets that we need to make this vision a reality. We have a chance as theorists to get started a little bit early on the process because we don't have to wait for the MV, the vacuum chambers and everything to be fabricated and installed and gotten up and running. So what we have out right now, an active call for theory proposals and fundamental enabling tools. So this is a little bit unusual. 95% or more of our proposal calls are going to be experimental synthesis user proposal calls. Having one which is a pure theory orientation is really a product of the ramp-up phase that we have right here. So what is the goal of this? The goal here is, as the experimental capabilities are ramping up, we want to anticipate what theory tools, what data sets are going to be useful. What do we want to have ready and waiting for the experimentalists when the experimental equipment is up and operating? This could mean, material-specific force fields. This could be new phase stability information. This could be continuum models that are describing some key properties of the synthetic conditions. This could be anything that's in the imagination of a potential theory collaborator or affiliate or member of the platform. Now, the support for this is actually quite limited in that this is primarily an experimental platform, and resources, as I said earlier, we're not a grant-making agency. So what are we envisioning here? We're envisioning the ability to support personnel over a time scale of 6 to 12 months. This is the time scale on which the experimental equipment would get up and running. Essentially, this is our window that we have here. Includes access to computational resources. So the ACI here is going to be bringing online some new computational resources in the fall, and the 2DCC will participate in that. We'll be able to provide access to computational nodes, and that could be both at Penn State or external, the computational resources. And especially for primarily undergraduate or minority-serving institutions, we will support travel and lodging for visits to the 2DCC. This is going to apply to the experimental users as well, but for theorists, this may also be useful to facilitate collaborations to face-to-face. Although theorists can work remotely, face-to-face is also useful. So that resource is also available. Now you can see the call for proposals on the 2DCC website, which is obscured on this slide. For some reason, it's up there at the top, 2dcc.psu.edu. And the submission deadline is August 31. We'll review these on a rolling basis, but we did put in a deadline there to give people a focus on preparing their white papers. These are very short. This is a short white paper style proposal. Don't treat this like an NSF proposal. It's a much lower impact activity. The key thing to emphasize here is close relationship to experimental efforts, synthetic efforts. So if it's a theory project that looks like a little theory sandbox, it might be a really interesting theory sandbox, but if it's not contributing to the mission of the two-dimensional crystal consortium, then it's just not a good fit. And the resources to support this are limited because most of our resources now are going into building up the experimental side of things. So we're going to have to be very selective in terms of what's supported. And there will be some give and take to this process to try to develop a coherent theory effort across all of the supported projects that the platform can accommodate. So I wanted to put up, for the benefit of any remote listeners, a list of, I didn't try really hard to make it exhaustive, but a list of some of the key collaborators, among others, at Penn State on the theory side of things, and a web of expertise. And so these are potential people, if you're an outside theorist or experimentalist interested in using the 2DCC, and you anticipate that you may have some theory interests in any of these areas, I encourage you to go to the website and you can look up all of these people and make contacts, or even potentially ask one of the executive leadership team in the 2DCC if they could recommend somebody to talk to. Okay, so I wanted to finish up and say that I want to hold a couple just informal lunches. I still have to choose a room, but this Friday and next Monday, essentially to facilitate team building and strategic planning and this theory effort that we're trying to ramp up to get some fundamental theory capabilities in place by the time the experimental equipment is up and going. As I said, we're sort of at this middle ground. We're not really a grant agency by any means. We provide in-kind support for no fee to some facilities. So although we do have external review, it's advisory, and we need to integrate all that information together and get a coherent plan going forward. So I have a couple lunch discussions to help try to facilitate that team building and planning experience. And then finally, so you can email me. My email address is up there if you're interested in attending that, or if you just have a question. And I encourage experimentalists to come as well. I just want to get some heads together around a table and do some brainstorming. And finally, I wanted to leave at the bottom here this final message here, that this is really very new, a user facility for material synthesis. So as we're designing our procedures and our access models for this, we're trying to envision what will be most effective in the end goal of achieving really compelling advances in synthesis. And this is going to be a process with continual self-assessment and the feedback of the user base or the potential users ongoing over the next several years is going to be very important. I wanted to start today on that. Recommend either online or offline as we go through this process of this initial call and going ahead from there. Any feedback, formal or informal, that you can provide will be of great value in the eventual success of the 2DCC. Okay, and I'm done.
Okay, so this is Kevin, your moderator. So anybody online that has a question, feel free to ask it in the chat box now, and we'll moderate the question through. If there are no questions online after about 30 seconds or 45 seconds or so, we'll go to the local folks to have them ask questions. So please go ahead and chat box your questions.
Oh, that's Audrey.
We have some coming in now. Then when the questions do come in, you can see them.
I'll see them right there, yes. Audrey, the reactive funding, how do you put it?
questions.
Okay, so question is the reactive funding, how do we put that in a proposal budget? Well, you can't really, right? So that's something that the need isn't, you can't see that. Sort of by definition, that's a form of theory support that can't appear in an initial proposal. So that's going to be ad hoc, essentially. The users will have some ability to direct resources in terms of theory activity, and it's not something that can be built in explicitly what kind of thing you would support reactively from the beginning. As we get user calls come out, we'll be confronting the precise implementation of that. So that is that's something that is going to sort of by definition be somewhat ad hoc as far as the deployment. We have some potential to anticipate there could be some kind of need and put things aside for that. But yeah, that's sort of intrinsically kind of fuzzy. Yes, there is. So can you reserve funds for reactive funding? Is Audrey's follow-up question on that? Yeah, we basically have to in a sense. So I don't want to speak to the precise budgetary mechanism of that. That's more I've got looking at Joan here for that. But yeah, I mean functionally we need to have something like that happen. Yeah. Or I realize there are questions of stability for various personnel who might be contributing towards the overall platform goals, and these are things we all have to figure out. To some extent on a policy level, to some extent on a case-by-case level. Okay, hopefully that was clear enough. Not crystal clear, but I think that's just because we're launching. We're still wrapping up. Okay, second question. Hi, Vin, is there a desire for calculations of functional properties? I would say yes. I guess my case study didn't get into that particular aspect so much, but there are one of the big experimental capabilities here is the in situ characterization, the ARPAS and the 4-probe and scan probe and optical characterization during growth and after growth. And in all those cases, there could be interpretation questions. And what does the result mean from that in situ characterization? So there's certainly a role for theory there. And there's going to be a lot of sort of, looking at specific cases in terms of figuring out how to facilitate that expertise getting deployed in the need of a given user. So there's going to be a lot of case by case on that issue, but on the general question of is there a desire for calculation of functional properties, I would say yes, and especially functional properties which are a key goal of the synthesis, right? You're synthesizing something because you want a particular property which you're measuring in situ to help guide the synthetic protocol. That would be most closely aligned. You could think beyond that as well.
Okay, if there's no more active questions in the chat box, we'll have some, if there's any questions for the local folks here, the local audience, please go ahead. Whatever question you ask, we'll repeat it. We'll get Audrey's next. Are there any local questions?
Suwin.
Yeah.
Could you illustrate the value for continuum modeling on this whole thing?
Yeah. Sorry, that was Oh, those bullets on the theory call slide. I wonder, do I actually have another? I'll go back to it. So those are just. That's not supposed to be exhaustive by any means. I was just trying to think of just sort of primers for people's brainstorming. So you could imagine things at the level of simulating the chamber. I know this is not what you have in mind right now, but you could imagine continuum at the level of the gas flow in the chamber and the heat flow and whatnot else, because that actually can be crucial. You can have cases where you can grow something in that chamber and you can't grow it in the chamber on the other side of the room, right? Even though the conditions are nominally the same, because there's something about the internal dynamics of those two chambers. I know what you're thinking more in terms of the continuum of the actual continuum mechanics of the actual material. The growth of one layer on top of a second layer where there's interactions between them. That's on the long length scales, you start getting continuum issues that start getting involved there. The interaction of one layer with the substrate underneath, right? Substrate is often crucial to the growth. Right? It's typically crucial to the growth, right? So the interactions with that substrate, any deformations on long length scales that might come out of that. The idea that growth is determined by things over a really wide range of time scales and length scales. Very fast processes and then much slower processes that are occurring on atomistic length scales or micron length scales all become important. The ultimate goal is wafer scale growth of a single crystal, single layer. Certainly at that scale, you can imagine some continuum issues coming up. And Joe?
Yeah, the lunch discussions, would you like experimentalists to come with, like a few slides talking about issues they have or things where, they could use theory support or
that would be wonderful. So yeah, Joan, in case the mics didn't pick it up, is asking at the lunch discussions if experimentalists can come. Yes. I haven't been sent out the sort of the emails yet to encourage people, because I didn't decide on those days until last night when I was making these slides. But yes, absolutely. So Joan knows that those questions I had on the third slide of the talk, that they came from the experimentalists. I pulled a group of experimentalists. And definitely, the idea there is that although we're going through this proposal system and getting external review on these this initial call, at the same time we want to have an overall coherence to what we're trying to do. It's pretty limited resources overall, and the theory side of things. So we want to be sure that they're used effectively, and that if we're supporting two different things or three different efforts, that they align with what we actually need long term in terms of the experimental side of the house, and they align to each other. So we want all those heads in the room and just try to hash out what makes sense. Have some of that before proposals go in, right? Anybody else?
Anybody else online have any more questions before we close out the session?
Thank you for listening.
Yep. And as a reminder, on August 30th will be our next webinar, same time, same bat channel. But on that